Pluto is a hidden, more distant world that is far away, a humble planet that once belonged to our closed planetary gathering. However, advancing and often obnoxious statements by Neil deGrasse Tyson, a leading astrophysicist, and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They propose that this cold world may be on a crash course with Neptune. But how should this, in fact, work, and what might be the consequences of witnessing such a massive event? Is it an enticing and valuable distinction, or is there something else to this approaching perpetual mishap? Join us as we inspect the probable consequences of a Pluto-Neptune collision. Pluto, a past planet that was later reclassified as a dwarf planet, remains a subject of focus and interest in the vast universe. As shown by ongoing estimates by leading experts, Pluto's orbit is hazardously close to Neptune's. Astrophysicists like Neil deGrasse Tyson and Michio Kaku are both alerting people to a potentially dangerous interaction between these two planets, which could pose a huge risk to Earth. But how exactly does such an event occur? Pluto's journey around the Sun is unlike that of any other planet in our nearby planetary group. It requires a stunning 248 years to complete one orbit. Since its discovery in 1930, it hasn't even completed a full revolution. But the fascination does not end there. Pluto's orbit is marked by its unusually elliptical shape, which contrasts with the almost circular orbits of the major planets. What makes Pluto's orbit even more extraordinary is its inclination. It is tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is considerably more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital plan. One of the most fascinating features of Pluto's orbit is its relationship with Neptune. For approximately 20 years per Pluto orbit, Pluto actually comes closer to the Sun than Neptune, defying our expectations from their positions in the planetary system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The solution lies in other gravitational influences, planets with which Pluto's orbit interacts. When Pluto's orbit was first studied shortly after its discovery, astronomers tried to figure out its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit, amid all these complexities, remains stable and avoids crossing Neptune's path. This stability is proof of the intricacies of celestial mechanics. The three-body problem involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence one another through gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. In Pluto's case, this demonstrates how the gravity of the Sun and Neptune work together in a complex way. The terms non-synchronous vibration, orbital precession, and the VZK oscillation are crucial here. According to astrophysicists, what keeps all planets in their orbits includes non-synchronous vibration. In the case of Pluto and Neptune, whenever Pluto enters the same region of orbit as Neptune, it is positioned about 90 degrees away. This spatial separation is crucial in preventing their orbits from merging. Orbital precession, on the other hand, describes the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune, or any other massive planet, it is positioned far above their orbital plane, offering an additional layer of protection from potential collisions. Another key factor is the VZK oscillation, named after three scientists who studied how objects move in space. It involves the gravitational relationship among Pluto, Neptune, and the Sun. This gravitational pull influences how they move. In Pluto's case, the VZK oscillation helps explain why its orbit near the Sun is so irregular. Despite Pluto's seemingly whimsical path, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation shows that, although space may seem turbulent and unpredictable, certain rules and patterns maintain equilibrium. These factors contribute to stabilizing Pluto's orbit, ensuring it doesn't crash into Neptune or drift off course. This three-body problem is critical to understanding how orbits change due to gravitational pulls. Studying this helps us learn more about Pluto, our local planetary system, and even distant worlds and their stars. Mathematical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is actually unstable. Minor deviations in starting conditions can lead to huge differences over thousands of years. However, these peculiarities have also been found to maintain stability over incredibly long timescales. Monitoring this disruption has been crucial. Later automated examinations have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto. The distance Pluto travels from the Sun to Neptune reveals a special relationship. Each time Pluto completes 2 orbits around the Sun, Neptune completes 3. This 3:2 resonance helps keep Pluto's orbit stable. However, Neptune isn't the only planet at play. Jupiter's gravity also plays a massive role in stabilizing Pluto. Saturn contributes as well. These studies show that Jupiter's immense gravity is powerful enough to ensure that Pluto stays on a consistent path for a long time. So perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without coming into contact with trouble. These peculiarities are essential in maintaining order and stability in the solar system. Without these elements, the solar system would be a much more chaotic place. Pluto-sized bodies could collide with others or be thrown out of orbit, launching a chain of events with other celestial bodies. Especially with discussions about Pluto possibly crashing into Neptune in the future, understanding its orbit is crucial. It gives a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates that even the most unstable orbits can reach a state of harmony through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and research into these phenomena to better comprehend our position in the universe. Investigating the depths of space often leads us to confront the strange nature of celestial bodies. Moreover, Pluto's orbit is an ideal example of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions. Pluto is a clear example of this. This means that even slight changes in the dwarf planet's position or speed can significantly impact its long-term orbit. Using computer simulations has been immensely helpful for scientists in determining how Pluto moves through space. These simulations use complex mathematics to model how Pluto and other objects, like Neptune, pull on one another. By tweaking small details in the simulations, researchers can see how even minor changes can greatly affect where Pluto ends up. In the late 1980s, these simulations revolutionized our understanding of orbital mechanics. Scientists discovered that even tiny variations, such as the slightest shift in Pluto's velocity or position, could, over time, produce vast differences in its orbit. This sensitivity confirmed that Pluto's orbit, while appearing stable in the short term, is governed by chaotic dynamics over astronomical timescales. Despite this, Pluto has managed to avoid disaster thanks to the stabilizing influences of orbital resonances, particularly the 3:2 resonance with Neptune. This gravitational dance ensures that although their orbits cross paths in space, Pluto and Neptune never actually come close to colliding. This elegant synchronization keeps Pluto safe and reaffirms the surprising order that underlies the apparent chaos of the cosmos. Furthermore, long-term computational models suggest that this resonance could remain stable for millions of years, perhaps even billions, unless disrupted by an external force, such as a rogue object entering the solar system or an unexpected shift in planetary alignment. But the question remains, what if something did disrupt this balance? Astrophysicists have modeled a range of what-if scenarios, from a passing star altering the solar system's gravitational equilibrium to a large, undiscovered planet, sometimes referred to as Planet 9, exerting influence on the outer solar system. In such cases, Pluto's delicate orbital harmony could be shattered, potentially leading to dangerous outcomes, including close encounters with Neptune or even ejection from the solar system entirely. Such events, while highly unlikely, are not outside the realm of possibility. The solar system has experienced countless gravitational upheavals since its formation 4.6 billion years ago. Some objects have been flung into the distant Oort cloud. Others have been pulled into the Sun, or collided with planets, leaving lasting scars like those visible on the Moon or Jupiter. Pluto's continued journey through space is, therefore, a testament to the dynamic and ever-evolving nature of our celestial neighborhood. Its orbit, eccentric, inclined, and chaotic, remains a powerful reminder that our understanding of space is still unfolding. In conclusion, while the idea of Pluto colliding with Neptune may capture the imagination, the scientific reality is more nuanced and fascinating. The complex ballet of gravitational forces, orbital resonances, and chaos theory paints a picture not of impending disaster, but of a cosmic system finely balanced by invisible forces. As we continue to observe, model, and explore, we unlock not just the secrets of Pluto and Neptune, but the greater mysteries of the universe itself. Demonstrated something. Despite the fact that Pluto's orbit has characteristics like non-synchronization, to maintain vibration and orbital progression, Pluto's orbit can still be stable, unpredictable and erratic when you begin with even a slight variation in its location. Whether Pluto is off by position or speed, its orbit may eventually appear completely different after just a few years. Despite this chaos, Pluto's orbit continues and persists for very long periods of time. This essentially took billions of years, signifying that Pluto's trip around even the Sun has a certain order to it, though it seems violent at first. Predicting celestial events, especially when they involve erratic orbits like Pluto's, presents a significant obstacle. The unpredictability of these systems indicates that forecasts for the future are frequently filled with ambiguity. While mathematical models provide excellent tools for understanding and predicting the upcoming routes taken by celestial bodies, they also highlight the limitations of our ability to predict. These models rely heavily on the precision of initial circumstances, and any minor error or distortion can result in enormously different outcomes, making precise predictions a daunting task. Moreover, planetary orbits, like Pluto's, being chaotic reminds us of the ever-changing, dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case reminds us how much our current understanding of the universe remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential crash between Pluto and Neptune? Despite all of this, complex forces are attempting to stop such an occasion. Neil deGrasse Tyson, a well-known astrophysicist and a key figure in promoting cosmology, offers a unique perspective on our solar system's unsolved mysteries, especially the intriguing case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful views on the evolving nature of celestial mechanics and the public's interest in previously neglected areas of space. Tyson's position regarding the renaming of Pluto is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a diminishment, but as an important adjustment in alignment with our growing comprehension of the various bodies circling our Sun. His approach to celestial mechanics is one of continuous learning and change. He views the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The fascination with these questions keeps space exploration so compelling. However, despite Tyson's confidence, his thoughts on Pluto, and the potential impact on Neptune, illustrate his concerns regarding the future of Pluto's orbit. This suggests that there might still be more secrets to uncover. Will Pluto collide with Neptune? Or is this just another moment of confusion in the constantly changing universe of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We keep studying these celestial phenomena with the hope of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises yet another question about the enigmatic and captivating universe in which we exist. The fascinating issues that Pluto and Neptune raise challenge traditional understandings of the solar system's dynamics and the stability of planetary orbits. The notion that two celestial bodies with such incomprehensibly different properties could collide is both unsettling and intriguing, especially considering the current relative strength of their orbits. Given that Pluto is in the farthest reaches of the solar system, far from the other planets, and Neptune is itself a massive gas giant with a powerful gravitational field, the implications of such a collision would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two. Despite being a dwarf planet, Pluto is made up of many different elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made mostly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is primarily composed of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would drastically influence their behavior and structure, potentially creating an event visible across great distances. What makes this possible? The hypothetical impact, particularly the influence of other planets and bodies in the solar system, is enticing. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it isn't the only consideration. The presence of Jupiter, the largest planet, is another important factor. Jupiter's enormous mass and powerful gravitational pull provide a stabilizing effect on Pluto's orbit, blocking it from straying too far into Neptune's domain. Likewise, Saturn's gravitational influence further complicates the dynamics of the outer solar system, reducing the likelihood of a catastrophic event between Pluto and Neptune. Still, even with the reassuring gravitational dance among the outer planets, the concern isn't entirely misplaced. The solar system is not a fixed structure, it's a living, shifting entity. Orbits evolve over time. Minute changes, occurring over millions of years, can ripple outward, subtly nudging celestial bodies into new paths. This is especially true for objects like Pluto, whose elongated and tilted orbit already defies typical planetary motion. The possibility of a future in which Pluto and Neptune approach dangerously close might sound far-fetched now, but in the timeline of the universe, where a billion years is merely a chapter, such a scenario becomes less improbable. It doesn't necessarily mean a dramatic crash, but gravitational interactions, orbital resonances, or near misses that shift the balance ever so slightly. What adds even more intrigue is Pluto's 3:2 orbital resonance with Neptune. For every 2 orbits Pluto makes around the Sun, Neptune completes exactly 3. This gravitational rhythm is a cosmic safety net of sorts, ensuring that the two bodies never actually collide, at least, under current conditions. But scientists know that resonances, too, can break over time, especially under external influence. The passage of other massive bodies through the outer solar system, like hypothetical Planet 9, could alter everything. Could an unknown force disturb this delicate balance? Astronomers continue to hypothesize the existence of distant, as yet undetected celestial objects that may influence outer planetary orbits. These forces might be subtle, buried in the math of perturbations and gravitational nudges, but their long-term effects could be profound. A single large object, passing through at the right angle, might destabilize the resonance between Pluto and Neptune. And then there's the issue of human limitation. As advanced as our simulations and models have become, they're still bound by the assumptions we make and the data we currently possess. Our window into the cosmos is growing, but still narrow. There may be entire factors unaccounted for, forces we don't yet understand or observe. Why does this matter? Because the study of Pluto and Neptune's relationship is more than just theoretical curiosity. It's a mirror reflecting our vulnerability and our ambition. As we explore the outer limits of our solar system, we begin to grasp the complexity of cosmic mechanics, the interwoven paths that connect even the farthest worlds. If something as distant and obscure as Pluto can still hold secrets, perhaps even the potential for catastrophic collision, then what else lies beyond our current perception? In this way, Pluto reminds us not only of how much we've learned, but how much still waits to be uncovered.